Hi everyone, this is Irene Zapata, and today we are going to discuss Chapter 5, Section 3, and focus mostly on differential equations of growth and decay. By reviewing that, and this may seem that is a great jump from Section 2 that we did already, that we completed already. It is not, and it's not because things are not that complicated as they sound. So let's say it together. What we discussed last week were different equations of the form like the one that you see on your screen. The derivative of y is equal to negative 400 times e to the negative 0.04 times x. So basically what you were doing is you were considering the function f of x to be nothing else than, name it y, and instead of saying f of prime is nothing else than, if f of x of course is equal to, if f of x, let me write right here, if f of x is equal to, in this case, y equals to negative 400 e to the negative 0.04x, then f prime, the derivative of that, would be nothing else than y prime. That is going to be the derivative of negative 400 times e to the negative 0.04x. And if we apply the chain rule here, the result would be nothing else than negative 400 times negative 0.04 times e to the negative 0.04x. And of course then you will simplify and calculate that. Well, the fact that we have two variables right here, the one is the y and the other is the x, it enables us to call those differential equations. And a differential equation is nothing else than an equation that involves an unknown function and one or more of its derivatives. So the unknown function right here is the y prime. It's going to be the derivative of this function. And it is an equation because you equate this derivative of the unknown function to something that is nothing else than a known function on a different variable. In the same way, of course, this is a different notation. I want to remind you that this, again, is nothing else than the derivative of y in terms of x. Now, this, in terms of the notation and explanation of how we read this type of equations. And continuing with notation and terminology, right here I want us to see how we differentiate between a first order and a second order differential equation. Before you start wondering what type and how far we will go with differential equations, I can tell you that we're not going to look into second order differential equations in our class. We will focus mainly on very simple first order differential equations. So when we say first order differential equation, this means that we involved only first derivatives. So if you have the function y, then the derivative of the y, the first derivative of the y will be y prime. Or if you want to denote it with dy over dx, right, over the variable x. So if you have the function, let's say f of x, that is nothing else, something like simple, 2k to the third, then if you consider the f of x to be equal to y, then if you look at y prime to be equal to 2x to the third, then right here, or the derivative of 2x to the third, then this is going to be equal to 6x squared. Then you can rewrite that as y prime equals to 6x squared, and this now will look like a first derivative. Again, the difference between first derivative and second derivative is nothing else than involving in your equation only first derivatives of a function. While as you can see right here, we have in our equation also a second derivative. So let's see now what we mean when we have a differential equation and we try to solve it. What exactly is a solution of a differential equation? Well, a solution for a differential equation is nothing else as a solution for any type of equation than some kind of an entity that if you substitute it for your variable in your equation, satisfies this equation. Now, the difference right here is that the differential equations have solutions that are not numbers, but they are functions themselves. So, the whole point right here, when you solve a differential equation, what you do is you are looking not for a number, not for an angle, like in trigonometric equations, but for a function. And this is what makes differential equations a little bit complicated. They are complicated because for any other kind of equations, you can guess, you can visualize, because you are talking about numbers. When you work with differential equations, it is harder to visualize the solution because you are referring to functions. So finding a solution for a differential equation, it can be difficult or it can be even impossible. What does this mean? It is possible that we don't have a solution for a differential equation, first of all. So this makes the equation impossible, right? There is no such solution. To be difficult, it's something that we can solve, but maybe we can need different tools, different type of processes, some theorems possibly that we need to know upfront in order to perform them, to apply them, to solve the equation. So let's look together at an interesting but simple example in order to understand a little bit better what does it mean to try to solve a differential equation. So let's look at the example that you see on your screen. That is what? It's a function. What is this? This is a function. Now look at the question, be careful. The question doesn't ask you what is the solution of the function, but what it asks you is this, meaning let's call this A, is this an actual solution of a differential equation? So you say this to be a solution to an equation. That equation would be a differential equation. So right here what we are trying to show is that is this y equals to 5x minus 19, this function, is this a solution to this equation? This right here is a differential equation. How do we understand that this is a differential equation? Well, first of all, it involves right here a derivative, first order derivative. So this is a first order differential equation. Okay. Okay, in the same format, you may see a differential equation that looks like this. Okay, this equation and this equation, these two are equivalent equations. They have the same solution. Okay, so we are going to take these and try to solve it. We will solve this in order to find out if this y equals to 5x minus 19 is a solution for this equation. Okay, let's do it together. So let me rewrite again the information here just to make sure that we understand what we are trying to do. We have the following differential equation: x minus 3 times the derivative of y in respect to x equals to y plus 4. This is my differential equation. Now, what I'm looking for is I try to see if the following function, y equals to 5x minus 19, is a solution. Is this a solution for, let's call this now b? Is this a solution for b? That's the question that I try to solve. Okay, how do I do that? Well, let's look at this function right here. That's your y, right? So let's find, first of all, everything that we need to know. So the first thing that I want to find is the y prime. Remember, the y prime is nothing else than dy over dx. So what is this going to be? Well, this is going to be the derivative of 5x minus 19, correct? Okay, and what is this? This is equal to 5. Just 5. Okay, good. So if this function right here is a solution for b, so if this function right here is a solution for b, then this means that if I replace the y right here, wherever you have a y here, with this, then the left side is going to be equal to the right side, because this is what defines an equation, correct? Okay, let's do it. So what I'm going to do is I'm going to take the b and replace now the y's. Well, x minus 3 stays the same, but as you can see right here, and maybe I need to get that one, instead of having dy over dx, I'm going to multiply this by it equal. And what is it equal? Well, the 5x, right? So I replace that with the derivative of dy over dx, that is 5. Okay, I leave the rest of the equation, the parts of the equation that I had from b before, and I replace what? Only those parts that they have to do with y. So what is the y now here? Well, the y, if this is a solution for my b, then the y, if I replace this y with 5x minus 9, minus 19, then the left-hand side of b must be equal to the right-hand side of b. Okay, so what I need to do now is verify. So I have 5x minus 15 equals to 5x minus 19 plus 4. So this means that 5x minus 15 is equal to 5x minus 15. So this means that this is correct. And it is correct. Why? It is correct because the left-hand side is equal to the right-hand side. So what does this tell me? This means that y equals to 5x minus 19 is a solution for b. So right here I verified a solution for this equation, for this differential equation. So what I would like us to see now is, why do we care? What type of implementation, application do we have for differential equations that they are related with our professional or personal life? So let's look at an example. You know about compound interest, and you know until now how to calculate the interest. You probably remember that when you have a compound interest that increases over time continuously, I want to remind you the formula, then the formula that you have, and this is one of the formulas, right? The formula that you were using for compound interest was that. And what was that? Well, if you have an initial principal, P0, let's suppose that you have $1,000 that you put in the bank. And suppose that you have a very good bank that gives you back as an interest continuously. It compounds your interest continuously. These type of banks do not exist. But nevertheless, assume that that was the case. Then R is the rate. You remember, this is the rate the annual rate of interest, and T is how long you have to leave your money in the bank in order to get the interest. So the P is going to be the principal, the amount of money, let's say dollars, after T years. After T years. So what you are seeing right here is a formula that gives you how much money you will get, you will have in the bank after, let's say, 11 years, if you initially put in your account $1,000 and you have a rate, let's say, of 5%, and this is how you calculate it. Now, you can manipulate this formula and to calculate not only how much money you will get after 11 years, but let's say if you have an account that you don't know how long you have this account, but you know that you put $1,000 at the beginning of the account, and you know the rate that this account gave you, then you can calculate how many years you had that account. So you can solve basically this equation for any one of those variables, R, T, P, or even P0, okay? And we have done this until now. We have solved this type of problems. There is, though, another type of problem that banks are interested about. And this, it doesn't have a solution that is just a number. So it doesn't solve for one variable. You don't care about the rate or the time or how much money you will have at the end or how much money you will have at the beginning. What you care about is how much money you have at any given time. Wait a moment. What does this mean? I want to know how much money I will have at any given time from today and 11 years from today, 2020 to 2031. Well, how do you solve that? If you think about this equation, whatever the equation is, we don't know yet what the equation is. This equation will not give you one solution, but will give you a vector of solutions, many different solutions. How many? Well, if we have 365 days per year times 11 years, it will be around 4,000 different numbers. Okay, fine. A 0 up to 8,000, let's say 4,500. All the days. Okay, how do you find this? Well, the first thing that you need to realize right here is that a single equation, it gives you as a solution one number, specific number. While this type of problem, it requires you to be solved and give you as a solution a series of numbers. Now, this series of numbers that you get can be nothing else than points of a curve. Okay? If they are points of the curve, let's say that this is the type of the curve. Of course, these are my money, so I really want them to look like this, exponential type of curve. Then immediately, this means that these are nothing else than points that they express a function, some kind of a function f. What is this function? This is going to be the solution to my problem, to the problem that I started with, right? So you are looking now for a function. The function is what will determine how much money you will have in your account at every given day for the period from 2020 to 2031. This requires you to solve a differential equation. Okay, let's look now more carefully what exactly does this slide say. If you have an amount P that represents the initial amount of money, the money that you have at the beginning of your account, let me make it into P0 because we are used to have P0 right here, okay? So if you have this money in your account deposited, and A is nothing else than the balance of the account at any time t. Now you see the any time. This is where the solution becomes a function. Then what you need to know is how to calculate this function. What is this function? This is A of t. What is A? A is P. is the amount of money that you have in your account at any given time t. Okay? Okay, good. Now, if you know the rate of growth of A with respect to t, meaning assume that you know that it grows exponentially and it follows the continued compound interest formula, then you know that the derivative of A is going to give you a solution for your equation. So, what we are looking for is a solution that is going to be a function at that satisfies the above conditions, meaning the derivative of that function must be the rate of growth of the amount of money that you start with respect to the time that you leave this amount of money in your account. Complicated enough? Yes, but I can give you the actual solution. I can give you the actual formula, and once you have the formula, things will become a little bit simpler, right? Okay, let's see that. So, in order to look at the problem, let's understand what exactly is happening. The derivative of the A, the function that gives us the money that will be in the account at any given time throughout these years, is going to be equal to R, that is the rate, times the money that you start with, the A, times the function A, the function that determines how much money will be in the account. Well, in order to obtain now this, what you need to try is to solve this equation. Okay? Now, is this an equation that is a differential equation? Well, as you can see, on the one side, I have a derivative of A, and on the other side, I have the function A itself. So, yes, it is a differential equation. So in order to, what you need to do in order to solve that is to work with the tools that you already know. This is equal to RA. If I divide by the function A from both sides of the equation, then what I have is d of A over dt equal 1 over A is equal to R. So this is what I have. And what I want is to solve this equation. Now, the easiest way to solve this equation is by taking the integral from both sides of the equation with respect to time. Okay? So, with respect to time. And in order to do that, what I get is, on the one side, 1 over A times d of A, and on the other side, I take the integral of R dt. Okay, so you see how I come to this point on my equation. Now, the integral of 1 over A times dA is nothing else than ln of the absolute value of A. And this one is simple, it's just RT. So this is how I get the ln of A equals to RT. And of course I need to add my C, that is the constant that I always add whenever I solve integrals. So at the end, the solution that I get is that the ln of A is equal to nothing else than RT plus C. Okay, and this is how I solve the equations for compound interest. Okay, now that we have seen that, what we want to do is basically and also understand how to apply that in a specific problem. So we will see that together.